Hi guys, AP Chemistry topic 8.3, weak acid and base equilibrium. So the objective today is to be able to explain the relationship among pH, pOH, and concentrations of all species in a solution of a monoprotic weak acid or weak base. So remember that for something to be considered weak acid or weak base, it does not ionize completely when it's put into solution. So we're dealing with equilibrium again, which you should know already from last unit. So there are a couple of equations to look at. So you have a K sub A and a K sub B. We'll talk about those, how to use those. So hydronium ion times the anion over the weak acid concentration. For K sub B, it's a hydroxide times the HB plus over the concentration of just B. So B represents any base. pKa, which we're going to talk about pKb, it's a negative log of those Kas and the Kbs, which you will be able to calculate in a bit. So weak acid, there are 6 strong acids we talked about: hydrochloric acid, hydrobromic, hydroiodic, perchloric acid, sulfuric acid, and nitric acid. All other acids are considered weak, like I said last lecture. So when a weak acid is dissolved, only a small amount of ionization will occur. So we're going to have to determine that amount. It's called percent ionization in a bit. So H sub A, any acid plus water produces hydronium and then the anion. Excuse me. So your equilibrium constant is associated, it's called the acid ionization constant. That's what we're going to use, a K sub A. So since these are very small, we're going to use something called a pK sub A, and that's kind of like the pH, but not really the pH. It's the same calculation. So looking at this diagram, a field particle diagram, so most HA molecules kind of remain intact, while very few ionize. So the weaker the acid, the less ionized particles you should be seeing in the solution, or in your diagram, if you will. Weak bases. So remember that your strong bases are anything. Oops, forgot. So strong bases are your group 1 and group 2 hydroxide. So lithium, strontium, calcium, all that. All other bases are considered weak. So when it's weak, only a small amount of the base will react with water to produce hydroxide. Again, it's just kind of the same concept with acids and bases, just, they're acids and bases. So they may ask you in a question, in a solution, which will most likely be present in the greatest amount. So they may say, oh, so we have this weak acid or a weak base, and it has a given concentration. And then it will ask you, which of the following will be in the highest concentration? So most likely it's going to be your acid or base, because they do not completely ionize into solution. So percent ionization, we're measuring the extent of ionization of an acid. So if it's a strong acid, it's going to be 100% ionization. While it's weak, it's going to be much lower, and here's how we concentrate it. It's your hydronium concentration at equilibrium divided by your initial acid concentration times 100. This is dependent on the strength of the acid or base and the initial concentration. So if acids are equal concentration, the weaker acid will have a lower percent ionization. Okay. The pKa of hypochlorous acid HClO is 7.54. What is the pH of a 0.100 molar solution of HClO? So we have a lot to do here. So we have a weak acid. So we have to know what it breaks up into. That will give us our equilibrium expression. And from there, we have to do a couple of calculations, including a nice table to find out what is the pH of something. So, excuse me. So, first step, hypochlorous acid plus water will produce hydronium ion plus the hypochlorite ion. This will give us my expression, equilibrium expression. So K sub A, because this is weak, hydronium ion times ClO1 minus over 8 concentration of HClO. So we can actually calculate the Ka by seeing that we're given the pKa. So remember that pKa is a negative log of the K log of Ka. But because I have the pKa, I need to find what the Ka is. So I'm going to do the opposite, kind of like before. And it's going to be 10 to the negative. So the Ka will equal 10 to the negative pKa. So 10 to the negative 7.54 gives me 2.98 times 10 to the negative 8. Now we can use an ice table to set up in order to solve the equilibrium concentration of the hydronium concentration. Hydronium ion, sorry. So we have ice. Okay, so we have HClO aqueous. We know the water. Oops, that's ugly. Water doesn't do anything. So hydronium ion plus, plus ClO1 minus. So we have 0.100. We're going to assume that our hydronium and hypochlorite ions are 0 like before. They all decrease or increase by x because they're all 1 to 1 to 1 ratio. So minus x plus x plus x. 0.100 minus x, x, and x. So again, this is all like before. So K sub A, I'm going to do it this way. Because we already have that in number 2. So 2.9 times 10 to the 8 equals x times x over 0.100 minus x. So we know that because our K sub A is small, is less than 1, we can assume it's negligible, or we can use our calculator. So x equals 5.4 times 10 to the negative 5. And since x equals the hydronium concentration already, and that equals that, we can assume that we can use that to get the pH. So the pH is negative log of the hydronium ion concentration, or negative log of x. So 5.4 times 10 to the negative 5. Probably should have rewrote that somewhere. So pH equals negative log of hydronium concentration. This equals my pH, so it's going to be about 4.27. Whew, that was exhausting. All right, so again, not too bad. It's kind of taking a lot of things you all know already, but at the same time, kind of expanding a little bit on it. You know what I'm saying? All right, very good. So calculate the percent ionization of 0.155 molar solution of acetic acid HC2H3O2. The K sub A, the Ka of this is 7.6 times 10 to the negative 5. So what we need to do first is recognize that need to find the concentration of the hydronium ion at equilibrium. So what does that mean? It means we got to do a lot of what we did the first time. Instead of finding the pH, we're finding the percent ionization. So I'll give you all a minute so you can stop the video if you'd like, so you can work on this particular problem. Again, a lot of it is a few steps from the previous example we just did. Okay, so step 1. Recognize what is my reaction. So acetic acid plus water will produce hydronium ion plus an acetate ion. So what is my expression? K sub A, which equals 1.76 times 10 to the negative 5, which equals the hydronium ion concentration, C2H, the acetate ion concentration divided by the concentration of acetic acid. Next, you got to find your concentrations. So we got to find the concentration of the hydronium ion at equilibrium. It means we have to do a nice chart for that. So we have ICE over here. We got our acetic acid, water, doesn't factor in, hydronium ion, and then acetate. So our initial concentrations are 0.155 molar. Oops. The other two are at 0 because we don't talk about it. We don't talk about it. Whatever. I don't want Disney to see me. So how did these change? They all change by x, either by adding or subtracting. So minus x from the acetic acid plus x for the other two. Or choose. Again, fairly similar. This should be almost second nature to y'all if you had been paying attention during Unit 7. So now we have to solve for x because that's going to give us our hydronium ion concentration. I may need to rearrange this at some point. Let's see. So x times x over 0.155 minus x, that equals 1.76 times 10 to the negative 5. You can use your calculator. You can assume the minus x is negligible and so just solve for x squared or x. X is 1.64 times 10 to the negative 3 molar. So this says that my hydronium ion concentration is 1.64 times 10 to the negative 3 molar. So to find the percent ion concentration, okay, where am I going to put this? Do I have enough space? That is my question. So I'm going to erase the top two steps and then we'll go from there. Okay, so step 5, percent ion concentration. So the percent ionization, equals the concentration of hydronium ion at equilibrium over the initial acid concentration times 100. So 1.64 times 10 to the negative 3 over 0.155, those are both molars, so they'll cancel out, times 100. That will equal 1.06%. I know it's a lot of work, a lot of steps here, obviously, in your problem set for this topic. You do have to make a couple of ICE charts, I believe, so get in the habit of it. It'll make it so much easier once you figure it out, type of thing. Once you get it, like, this one shouldn't be a problem at all. So, if you have any questions, please let me know. Thanks.